Okay, good day everyone. My name is Leung Xiang Wai, and today I will be presenting my final project in this semester, which is MECR 2323, malware analysis. So the title of my presentation is AI-assisted behavioral malware analysis and by enhancing sandbox triage and mirror attack mapping for modern malware detection. This topic focuses on how artificial intelligence, especially machine learning, uh, and LLM, large language model based reasoning, can support malware analysis in interpreting sandbox evidence, mapping malware behavior to mirror attack, and producing detection ready outputs. The aim is not to replace human analysis, but to improve the speed, consistency, and operational value of malware analysis. So let's move to the next. This presentation follows a problem to solution structure. First, I will explain the current problem in malware analysis and why traditional methods are under pressure. Then I will discuss the current technology, the technology trend of AI assisted malware analysis. After that, I will introduce the proposed framework, including evidence collection, AI assisted reasoning, attack mapping, and also the analyst validation. I will also include a safe technical case illustration to show how observed malware behaviors can be transformed into structured detection knowledge. Finally, I will discuss the operational value, benefits, challenges, governance considerations, and also the key takeaways. So modern malware analysis increasingly requires behavioral level intelligence, uh, not only static indicators such as hashes or strings. Traditional traditional signature-based detection is still useful, but it becomes less effective when malware authors frequently change file hashes, use packing, encryption, obfuscation, or dynamic API resolution. These techniques reduce the value of simple static inspection. In addition, some behaviors only appear at runtime, such as process creation, registry modification, file dropping, or command control communication. Therefore, defenders need to understand not only whether a file is malicious, but also what the malware actually does. This is why malware analysis is moving from isolated artifacts towards behavioral profiling. A behavior profile is more useful because it helps threat hunting, detection engineering, incident response, and mirror attack mapping. The current technological trend is the use of AI as an argumentation layer above existing malware analysis techniques. AI-assisted AI-assisted malware analysis is not a single tool. It is a workflow that combines machine learning, large language model reasoning, sandbox evidence, and also structured knowledge bases such as mirror attack. For example, AI can assist reverse engineering by summarizing the compiler output, identifying suspicious control flows, and supporting malware classification. It can also summarize long sandbox reports by converting process, registry, file, and network traces into concise behavioral narratives. More importantly, AI can help translate technical evidence into attack style techniques and procedures. This supports security teams because the output becomes easier to use for detection engineering and threat intelligence. The main shift is from asking, is this file malicious, to asking uh, what behavior does this sample express, how confident we are, and what should defenders do the next. So we come to the traditional analysis for its strengths and also limitations. So Static analysis, dynamic analysis, and automated sandboxing are still essential in malware analysis. However, each method has limitations. Static analysis is safe and fast. It helps analysts collect hashes, file type, PE metadata, strings, imports, and other indicators. However, packing and encryption can hide the real capability of the malware. For dynamic analysis, it's useful because it reveals runtime runtime behavior such as processes created, registry keys written, files dropped, and network connection made. However, malware may delay execution, detect virtual machines, or require certain conditions before activating. Uh, for the automated sandboxing, it will provide scalable and repeatable telemetry, but sandbox reports can be long, noisy, and incomplete. This is where AI can help. AI can summarize evidence, correlates weak signal across tools, and prioritize suspicious behavior chains. However, AI should be used after evidence collection. It should not replace safe malware analysis practice or analyst judgment. We come to the proposed framework. So this slide presents the proposed framework for AI-assisted behavioral malware analysis. The framework starts with the malware sample or inputs such as PE files, scripts, documents, URLs, or sandbox reports. Then the evidence is collected through static analysis, dynamic analysis, and also the sandbox telemetry. Next, the important features and behaviors are extracted, such as API calls, strings, network indicators, file events, registry changes, and process events. These are then passed into the AI-assisted reasoning stage, where the system helps summarize, correlate, and prioritize the evidence. After that, the observed behaviors are mapped to mirror attack tactics, techniques, and sub-techniques. However, the most important part of this framework is analyst validation. The analyst must review the AI-generated interpretations, check the evidence, assesses confidence, and control false positives. Only after the analyst done the validation, then it should validate the final operational outputs, such as the Yara or Sigma rules, attack layers, triage nodes, and detection recommendations. So for the evidence collection, what AI should read. So AI assistant is only as reliable as the evidence supplied to it. The evidence package should include file metadata such as hash values, file type, P headers, section entropy, and compile timestamps. It should be also include static artifacts such as strings, imports, resources, suspicious APIs, and embedded configuration. For runtime behavior, the evidence should include process trees, drop files, registry changes, persistence actions, and network telemetry. Network evidence may include HTTP requests, DNS queries, command and control indicators, user agent strings, and protocol patterns. The key principle here is traceability. Every AI generated claim should link back to observable evidence such as hash, logline, string, screenshot, packet, API call, or even the sandbox event. So without traceable evidence, AI output remains only speculation and should not be used for operational decision making. So AI assisted reasoning is useful in four main tasks. So first is it can summarize long sandbox reports into concise behavioral narratives. This help analysts quickly understand and what the malware did. Secondly, it can correlate different evidence types. For example, It can connect suspicious strings, API imports, process events, and network artifacts into one behavioral chain. Thirdly, it can prioritize high-risk behaviors. This is useful when analysts are handling many samples and need to decide which ones require deeper investigation. So lastly is the AI can draft attack mapping suggestions. It can propose possible techniques based on observed behavior, but these suggestions must still be reviewed by a human analyst. So the boundary will be clear. AI output should be treated as a hypothesis. Analyst validation determines whether the finding becomes operational intelligence. So mirror attack provides a common language for describing adversary behavior. The framework is structured around three levels: tactic, technique, and procedure. A tactic explains why the adversary performs an action. For example, the malware may aim for executions, persistent defense, evasion, or command and control. A technique explains how the behavior is performed. For example, PowerShell execution, registry run, key persistence, web protocol communication, or process injection. A procedure explains what exactly was observed in the sample. This could be the asset command line, registry key, URL, process, or API call. This is important because raw artifacts alone may not be meaningful to every security team. Attack mapping transforms those artifacts into structured security knowledge that can be shared, compared, and used for detection coverage. So this slide shows a safe technical case illustration. It is not a live malware demonstration. For the first example, if a sandbox is log shows PowerShell.exe-enc launched from a macro, AI may interpret this as encoded script execution. This can be mapped to T1 T1059.001 PowerShell and T1027 obfuscated files or information. The operation action could be to alert on encoded PowerShell launched by Office processes. For the second example, uh, if a registry key run is written under HKCU, this may indicate persistent. This maps to T1547.001 registry run keys. For the third example, if the malware sends HTTP requests to suspicious paths uh, such as the path of a gate.php or favicon, this may suggest command and control communication or payload retrieval. This can be mapped to the web protocols or ingress tool transfer. So another example would be the API such as create remote trade or uh, virtual alert X may suggest injection related capability, which can support mapping to T1055 process injection. Yep. So you put the next. The value of this framework is that it converts malware analysis into outputs that security teams can actually use. The first output is IOC, such as hashes, URL, domains, IP address, registry key, and file path. This can support immediate blocking and hunting. The second output is this detection rules, such as Yara or Sigma rules, based on validated strings, APIs, or any behavioral pattern. The third output is an attack layer. This allows the team to visualize which techniques were confirmed or suspected in the malware sample. The fourth output will be the triage nodes. These nodes explain the behavior, confidence level, and recommended next action in a concise analyst narrative. So the main idea is to move from artifact to behavior, from behavior to confidence, and from confidence to detection recommendation. This makes the analysis useful for SOC teams, threat hunters, detection engineers, and management reporting. So let's move to the next. So AI-assisted malware analysis provides several benefits, but it also introduces risks. One major benefit is faster triage. AI can help analysts process high-volume samples and lengthy sandbox reports from efficiently. However, the risk is that AI may generates unsupported explanation or incorrect attack mappings. The mitigation is to require evidence citations and analyst approval. Another benefit is better behavioral summarize for non-specialist stakeholders. However, sensitive malware samples or internal logs may expose confidential data if submitted to public AI systems. Therefore, private on-premise analysis and data minimization should be applied when required. AI also improved the connection between artifacts, TTPs, and detection actions. However, models may be biased towards common malware families or popular techniques. Analysts should compare AI suggestions with actual tool evidence and sandbox logs. Therefore, the academic position of this project is that the best approach is not fully automated malware analysis, but accountable AI-assisted malware analysis. So the first requirement is isolation. Malware samples should only be handled inside control virtual machines, sandboxes, or private analysis infrastructure. They should not be executed on a normal host machine. The second requirement is traceability. Every conclusion should cite the supporting artifacts, tool outputs, or log event. And the third requirement is privacy. Sensitive customer data and any internal telemetry should not be submitted to public platforms without proper approval. Another requirement is the accountability. Analysts should validate the confidence level, ambiguity, and false positive risks before the results are used operationally. In these frameworks, governance is not just an administrative requirement, it is the mechanism that makes AI-assisted malware analysis defensible and trustworthy. In conclusion, AI-assisted behavioral malware analysis is a practical evolution of malware analysis, but it is not a replacement for human analysts. The first key takeaway is that evidence must come first. Static, dynamic, and sandbox artifacts remain the foundation of credible analysis. The second takeaway is that AI can accelerate reasoning. It can summarize, correlate, and prioritize behaviors at analyst scale. The third takeaway is that mirror attack structures meaning it converts raw artifacts into shared statics, techniques, and procedures. The fourth takeaway is that human validation is mandatory. Final outputs must be reviewed for evidence, confidence, and false positive risk. The final takeaway is that operational outputs matter. IOCs, detection rules, attack layers, and triage nodes should support security operations and detection engineering. My final position is that the most defensible feature from malware analysis is evidence-led, AI-assisted attack structure, and analyst approved. Okay, so this slide lists the reference used to support the presentation in. So the source include official and credible materials such as ENISA, Trade Landscape, Microsoft Research Project, Mirror Attack Navigator, and NIST AI Risk Management Framework, and some recent academic work that related to the LLM assisted malware analysis. So these sources were selected because they support the key areas of the presentation, current malware traits, AI assisted analysis, attack mapping, risk management, and also responsible use of AI in cybersecurity. So that's all for my part today of this presentation. Thank you for everyone. Thank you for the time.